Hello everyone and welcome back to this Fall 2025 live stream for Physics 8A. This week is going to be week 2 and we're going to continue what we had started last week, which is kinematics, and we're just going to go ahead and generalize it to 2 dimensions. And that type of motion is a specific type of motion called projectile motion. So we'll dive into that. We'll do a quick recap, and I have something I want to talk about, which was a question I've gotten a few times now, so it's worth addressing. And we'll do a few problems to see how, projectile motion is, in a sense, similar to what we did last week, but also its own type of problem, and why it's a good problem for midterm 1, and you should probably expect a projectile motion problem. Just as a reminder, this live stream is going to be posted to our Facebook page, which you can find here, facebook.com/myslackademia. It is also posted on slackademia.com. If you go to the website and you look for the Physics 8A live stream, it's a free course you can enroll in. You'll find that all the live streams are going to be put there for the semester, along with the practice problems that we do during the live stream, so that you can attempt them and watch the solution if you want to practice. And there's also a collection of homework problems. So there's solutions to the homework problems, and I'm adding some every week. And the goal is to kind of build up a nice collection over time. So we're starting, this semester with the assignments, and we're going to build on that moving forward. But it's a free course. You should check it out. Definitely a good resource if you want kind of something to summarize each week of Physics 8A. And then, of course, for those of you who are asking, yes, you can either sign up for a study guide or masterclass. Masterclass has limited seats, so does the one-on-one tutoring. So if you want to get in touch and reach out, you can do so through Facebook. And sooner is better than later. I'm not pressure selling anyone, but just, my calendar does fill up pretty quick once midterm 1 starts to approach. So anyway, today is going to be projectile motion. Projectile motion is, it's kinematics, and it's a very classic type of problem on exams just because there's a lot of variety. It's all the same really, but you can make very creative problems, or just very realistic problems of launching a golf ball or throwing a rock or things like that. And we'll see that projectile motion tends to show up again and again as we go through the class. You think it's one and done. Once you're done with this chapter, you're never going to see it again, but actually you end up seeing it a lot just because it builds into other problems very nicely, even though it's its own little thing. So let's first to get started, let's give a definition, and then I want to touch on a question that I've gotten a lot this past week while we review kinematic equations. So projectile motion, it is the motion, we should say even, obviously this is about projectile motion, but let's be clear. Projectile motion is the motion of an object through the atmosphere while subjected solely to its weight. So it doesn't say that you have to launch the object from left to right or right to left. You could let it drop from a certain height. You could throw it down, straight down, without it moving to the left or to the right, as long as the only force acting on it as it falls is the weight force. Now what that means is that, for now, it's actually a terrible definition. I don't think we could have come up with a worse definition for week 2, because as it is, we don't know what forces are. So it's not a very good definition to go ahead and introduce force when we've never talked about forces and we can't define them and really don't know what's going on. So I do this because, of course, it is the formal definition, and the goal is that when you come back to see this video later, after you've learned about forces, or when you're reviewing for the midterm, then you have a definition that will make sense, and it will help you identify when you do or do not have projectile motion. But the idea is that typically we launch something like a golf ball or a cannonball, so it follows this parabolic path, right? But it could just be that the object falls straight through the atmosphere. The idea is that the only force acting on this object as it travels is the weight force. And again, we don't know what it is. I'm just going to write mg, and that hopefully will make sense later. Okay? And what dictates how far the object goes, how much time it spends in the air, the height that it reaches is the launch velocity, v0, and the launch angle, theta. In other words, after the object has been launched from this point, you can think of hitting a golf ball. It will travel like this through the air, right? And we neglect air resistance, let's say. And everything is dictated by v0 and theta, meaning once you've hit the golf ball, there is nothing you can do to this golf ball to alter its path. Its path is set. It will spend a certain amount of time in the air, reach a certain max height, and cover a certain horizontal distance that we call the range. But that is all set by v0 and theta. Now what you can't have, just to maybe explain a little bit what we mean by being subjected solely to the weight force, is you can't have, let's say, a rocket that has a thrust force F thrust. Okay? You can't have an object that undergoes air resistance. So we neglect air resistance typically in this class anyway, but you can't have air resistance F going this way, or you can't have a parachute, okay, force of parachute that's kind of breaking the fall there. None of that is okay. You have to think of, again, think of a golf ball or a cannonball that is being launched, and then once it's launched, the only thing we take into account is the weight force. And we can have a conversation as to whether or not we should account for air resistance, and if we did, we'd probably find that the path looks more like this, right? It's not symmetric. But it's very hard to account for air resistance, so typically we will not. We might not even tell you, oh, you can neglect air resistance. It's assumed that you just don't bother with it. Right? The only time you would bother with it is if a problem goes out of the way to mention air resistance and defines it and gives you a formula, then the point of that problem is to account for it. But typically that never happens, and typically we always therefore neglect air resistance. So that is the definition of projectile motion. And there's a few consequences to that we need to talk about and that are going to help us go over these kinematic equations. Okay, so let's do this. Because there's a few things that I want to touch on when we talk about kinematic equations. Let's recall, first of all, let's make this the x direction and this the y direction, okay? And then let's recall that last week we said that just by virtue of falling through the air, an object would have an acceleration downward of g, okay? Which means that really the y component, ay, should be minus g because we just went ahead and said that up is positive, so down is negative. Now that acceleration comes from gravity. It is there because the Earth has a mass and it exerts a gravitational pull on everything on or near the surface of the Earth, and so that is where it comes from. But gravity always points straight down, right? It points toward the center of the Earth, but if we're going to draw a flat little parcel of Earth here, it means that the acceleration due to gravity is vertical downward. So what that means is that with the same reasoning, we find that there is no acceleration along the x direction. There's no acceleration along the x direction because there's no force going at some angle, right? There's no force that would have maybe a component to the left or a component to the right. There's just with a weight force. And so as a consequence, again, this will make sense when we do Newton's second law, but as a consequence, the acceleration is ay is minus g and ax is 0. Okay? So that's for acceleration. Now remember that we also touched on components last week, and we're going to need the components of initial velocity. So this is v0 and this is theta, but v0 achieves two things. It launches the ball upward and to the right, and therefore it has two components. It has an x component and a y component, and the x component is why the golf ball gets launched to the right. The y component is why the golf ball gets launched upward. And there's two questions that I got a lot since last week. One was, how do you know which component is which? And how do you know if it's cosine theta or sine theta or whatever, which is fair? And then the other one is, more general question, how do you know what to plug into kinematic equations to set them up? So we're going to get to that. But first, let's talk about components. Okay. Now, components, you can think of components as the following. The component along x of v0 is the shadow of v0 along x. And the component of v0 along y is the shadow of v0 along y. Meaning that when it comes down to it, you're breaking up v0 into two parts, a horizontal part and a vertical part. And it has to be the case that if you were to assemble the horizontal part here with the vertical part like this, you have to get v0 back, right? So you're breaking it up into the part that's horizontal, the part that's vertical, and those are the components. And the components are always shorter than your vector, and they're dependent upon this angle here, which most of the time is measured relative to the horizontal, but sometimes we'll give you the angle relative to the vertical. You could do it either way, but it's very common to measure theta from the horizontal. So then, let me do this. I had just done this to visualize the two components, but I can move a vector around as long as I don't change its length and I don't rotate it. So this vector here is the same as this one, right? And I'm going to say that, well, this is the adjacent component relative to theta, so v0x should be v0 cosine theta, and then this is the opposite component relative to theta, so v0y should be v0 sine theta. But if that doesn't make sense, maybe it doesn't make sense yet. If you do it enough times, I promise you, you'll be looking at forces and velocity vectors and you'd be finding components very quickly and very easily. But let's say this is new and you're still confused as to how you would determine the components. Well, let's do the following. Let's just write what cosine theta is. Cosine theta is the adjacent side, that's v0 x, divided by the hypotenuse, which is v0. And if you multiply both sides by v0, you find that v0 x is v0 cosine of theta. Okay. You can do the same thing with the y component. The y component is going to be in terms of sine theta, but maybe you don't realize that. It's okay, just write sine theta. Sine theta is opposite, which is v0 y, divided by hypotenuse, which is v0. v0 y is v0 sine theta. And that's important because that's going to also answer this other question, which is how do we know what to put into the kinematic equations to set them up? Okay, so these are two important properties that come with projectile motion. This is non-negotiable. This is because of gravity, and the definition of projectile motion is we launch something through the atmosphere and therefore it moves through the gravitational field. Therefore, the acceleration will be downward with magnitude g. Acceleration along x is going to be 0, right? So speed along x is going to be 0, by the way. It's going to move at a constant speed in that direction. And then the x and y components of initial velocity, more often than not, wind up being v0 cosine theta for v0 x and v0 sine theta for v0 y. But again, if I give you a different angle, right, if I go ahead and I call this angle here theta, then that's going to change things around. I'm going to get sine theta along x and cosine theta along y. So you would always just, I would rederive these real quick, right, just to make sure. Okay, but those are going to be core to projectile motion, right? And projectile motion, again, so it's obviously it's motion, but it's motion along two directions at once. Right? The golf ball travels horizontally, but as it does, it also travels vertically. Its height changes, and it does both at the same time. And so it turns out that a nice way to describe how the golf ball moves is to do the following. So let me do this, right? And we're going to tie this back to what we learned last week. So I'm going to get rid of this. I don't need this. Okay, and I could, well, sure, I'll leave v0. Why not? That's fine. Let's get rid of x and y. We don't really need those for now. We already know what they are. Okay, well, the idea is that we're going to give what's called a parametric equation description of the particle's motion. So better said, we're going to use parametric equations to describe the motion of this golf ball. And these parametric equations are our kinematic equations. Right? So if you've learned about parametric equations before, this is going to sound familiar, but let's just real quick remind ourselves that what we're doing is we're not trying to find the function that describes y in terms of x. Instead, we're going to say, well, I'm going to tell you the position x as a function of time and the position y as a function of time. And should you have those coordinates at that given time, you will know exactly where the golf ball is. And in fact, if you have functions of time, x of t and y of t, you could plug in any time and you would know where the golf ball is all along. And you can do this not just with position, okay? In other words, not just with this x coordinate, which is x of t, and this y coordinate, which is y of t. You can also do it with velocity, right? Because velocity is going to look something like this. Velocity is always tangent to the path, so it's going to look something like that. It's a vector. It's going to have two components. It's going to have vx of t and vy of t. Right? And if I know both, then I can know how fast I'm going at any moment. I can know the direction in which I'm moving because I'll have components of this vector, which is the velocity vector. Let's call it v of t maybe. Okay, but I have to resort to components because I have motion in two directions at the same time. And so what I just do is I introduce functions of time that give me position and velocity along x and along y. And so this is going to tie to what we learned last week, because we said, oh, well, in the case of constant acceleration, which will always be the case in this class, then we have x of t and vx of t. We know what they look like, right? We said the following. We said that x of t is going to be 1/2 ax t squared plus v naught x t plus x naught. And then vx of t is just equal to, it's the derivative of this, but it ends up being axt plus v naught x. Now that was last week. Now last week we only had motion along one direction of space, but now we have motion along two directions at the same time. So I don't just need x of t, I also need y of t. Now y of t is going to be the same thing because I still have constant acceleration. 1/2 ayt squared plus v naught yt plus y naught. And then that means that we're going to have vy of t. Vy of t is going to be ayt plus v naught y. And last week I was saying that when you have kinematic equations, the goal is to find this, this, and this, because then you know everything. Same thing here, right? If you know ay, v naught y, and y naught, then you know everything because those terms are in here as well. And then you would know the four functions of time, meaning you would know the position of the golf ball at all times and the velocity of the golf ball at all times. So you'd be pretty happy with that. And the question that I got a lot was, well, how do you find these things? Like, how do you know what to do to find these things? Which is a fair question. So let's start with acceleration. Acceleration, for now, you have no way to find it. You will need Newton's second law. That is next week. So until next week, a sub x and a sub y, you don't know what they are. But that's actually exactly why we do projectile motion, because we then get to say, well, guess what? Ax is 0, ay is minus g. You don't have to know Newton's second law. I'm not asking you to derive these. I'm just telling you what they are. And that's always what it's going to be, because it's always going to be motion through the atmosphere, right? Where the only force is the weight force acting on this thing. So we know what ax and ay are. Okay. And then what's v naught x, what's v naught y? Well, we just talked about that, right? That's the x component of velocity, the y component of velocity. Now, a lot of problems launch the projectile from the ground up because you're hitting a golf ball or kicking a football or something like that. It doesn't have to be the case. You could be throwing a rock from a balcony, right? That would make your v naught y negative because the object would be thrown downward at first. So yes, most of the time this is what you get, but I would derive it each time just to make sure I don't mess up cosine or sine or the plus or minus. But the point is, the problem tells you enough information for you to find this. And if it's projectile motion, you don't get to argue this is acceleration. So the only thing that might be up to you is actually x naught and y naught. That's the initial position along x and y. And unless the problem places the origin for you, you can put the origin where you want. I would probably put the origin at the launch point here, right? Because if I do that, then I can say that x naught is 0 and y naught is 0, which is quite convenient. Doesn't always have to be true, but I could certainly write that. And then I could also say v naught x is v0 cosine theta, because I derived that above. V naught y is v naught sine of theta, because I derived it above. And I know what the acceleration is equal to. I know that I don't get to negotiate that anyway, because by definition of projectile motion, I have to have a sub x is 0 and ay is minus g. So this is ax is 0 and ay is negative g. And now I know everything. I know everything I need to establish the kinematic equations that will describe the motion of this projectile as it moves through the air. So if I sub all of this into these 4 equations, I'm going to get the following. I'm going to write them down here. Right? I'm going to get x of t is 1/2 axt squared is 0 because ax is 0, plus v naught xt is v0 cosine of theta t, and then x naught is equal to 0 in this case. Y of t is 1/2 ayt squared, that is minus 1/2 g t squared, plus v naught sine theta t, plus y naught is 0, so that ends there. And those are the kinematic equations for position. The kinematic equations for velocity are going to be vx of t is equal to actually just v naught cosine theta. Right, so we have constant velocity along x, right, which is important. Okay, it tells you that the shadow of the golf ball on the grass moves at constant velocity. Okay, so then minus gt plus v naught sine theta, that is vy of t. Okay, so these are going to be my kinematic equations. And now these very specifically are going to describe the motion here. You might tweak them slightly to adjust them to your problem, although it's very common to wind up with these anyway. But the point is, just like we said last week, if you're dealing with a kinematics problem, the first thing you want to do is set up the kinematic equations. And if you have more than one phase of motion, you set up kinematic equations for every single phase of motion. And so that's what we're going to do with projectile motion. That's going to be the same thing, just twice, because we need along x and along y at the same time. But it's not really double the work, because once you've done it a few times, it's really not that bad. And projectile motion problems are therefore great problems because they allow you to test 2 things at once. Along x, you have no acceleration, so you have uniform motion along x. And then along y, you do have acceleration. So if I give you a projectile motion problem on a test, I get to evaluate with one problem that you know how to do kinematics with no acceleration, and that you know how to do kinematics with acceleration. So it makes them very popular problems on exams, and again, you'll see projectile motion it's very easy to fit into subsequent chapters when you're solving problems. All of a sudden, a portion of the problem is projectile motion. All right, so with all of that said, let's try to apply this to a couple problems to see how this works. Now the first one, I tried to pick one that's you might find a little too simple, although I tried to make it interesting. But this is an old exam problem that I wrote a long time ago for some 8A students that were taking it in their post-bac. And then the second one is also a problem I wrote a long time ago, actually in the same context. It's just that this one's a little bit more interesting because it's well, it's a smidge harder. Let's put it that way, and it tells us, teaches us what to do if maybe you don't know the launch velocity v0 and how you would deal with that, which is actually a common occurrence in projectile motion problems. But let's start with this one. This one's good. This one is about Tony Parker, who was a basketball player. I don't think he is anymore, but he was. And he is jumping with an initial velocity v0 at an angle of theta is 50 degrees. And you can treat him like a particle because remember, the shape and size of objects doesn't matter. We just treat them as point masses. And just to be clear, this is not, this is not the ball being thrown so that it goes through the hoop. It is Tony Parker treated as a particle jumping forward and up into the air to get the ball to go through the hoop, but okay, this is not meant to represent the path of the ball, just so we're clear. Okay, so first question, just to be nice, set up the kinematic equations. You do it anyway, but I was trying to push you in the right direction. So let's set up the kinematic equations for Tony Parker's motion, and then what is the maximum height that he reaches? Classic question. Total time of flight, classic question as well. And then question 4 is a bit more interesting and a bit more midterm 1 level type level of difficulty. All right, so let's start with the kinematic equations. And to do that, I'm just going to make a quick copy of this so that I have it. Okay. And I can leverage a few things that we've already said, hopefully, to help me with this. All right, I already know a few things. So I know that AY is going to be minus G because I'm told that Y is positive upward. I also know that AX is 0. Yeah. Then here I know that the X component is going to be V0 cosine theta, and the Y component is going to be V0 sine of theta. And then as far as the origin of for X and Y goes, I'll just place the origin here, and that means that X0 is going to be Y0 is going to be 0. Okay, so I know how to write the kinematic equations, right? You see what I just said. A lot of the times you'll get exactly what I derived before because it is very common to launch a projectile from the ground up and to the right. So it's very, very common. It's not the only type of problem, just to be clear. You'll find problems that do it different, but it's very common, so we should not be surprised that we get the same kinematic equations that I derived before. Okay, now what will those be? Well, x of t is going to be v0 cosine theta t, and then y of t is going to be minus 1/2 g t squared plus v0 sine theta t. And by the way, once I have my kinematic equations, I can answer any question about the problem, right? Because it captures the position and the velocity as well as the acceleration of the particle or the object as it moves through the air. And so I can answer anything. I can tell you how high it goes, how long it spends in the air. I can tell you a whole bunch of stuff. So it's very important to get your kinematic equations set up, and I would actually encourage you, even though you could get Vx from x easily and Vy from y easily, I would just write them out like completely. I think it just makes a lot of sense to have everything. And it doesn't hurt anyway. And, it's good practice to do this for all problems because it'll help you see what you know and what you have. And then we can talk about how to use them. Okay, so then we want to find the maximum height that he reaches, and also what is the x location of that maximum height, which is okay, fair enough. Let me see if, no, that's not going to work. This will work. There we go. Okay, so let me put that down here just so that we have something to look at. And we want to find the max height. Now the max height is going to be somewhere here, but somewhere here is not going to cut it. I want to know exactly where this max height occurs. Okay. Now the question then is, let's call it the time t1. Okay, and the max height is going to be y, call it y max or y1, it doesn't really matter. Maybe I'll call it y max, right? And then this is going to be x1. Okay, the location at time t1 along the x direction. And we want both those things. Okay. Now, very important to realize, in kinematics, if you know time, if you knew t1, for instance, if somehow you knew t1, it would be very easy to get x1 and y max. You would get x1 by plugging t1 into this equation, and then you would get y max by plugging t1 into this equation. That is what these equations do. If you feed them time, they tell you x location and y location. That's what we want. So the idea is that if I knew time, I could solve the question. If only I knew time, how could I figure out what time is? Well, I can't say more than what I just said when it comes to x and y. But I can say something about Vx and Vy at the max height. So let me write this. Okay, this is the physics part, right? This is the hard part. At time t1, what is true? Our goal in physics is to write things that are true, because the answer is the answer. There's only one. And if we write enough things that are true, it's like all of a sudden out from the fog, these little pieces of answer show up, and if I put them together, I get the full answer. So at time t1, what has to be true? Well, it has to be true that x of t1 is equal to x1. It also has to be true that y of t1 is equal to y max. Hopefully we all agree on that. Okay, that has to be true. But something else must be true, because I don't know what t1 is, and this is not going to give me t1 because I don't know this and I don't know this. So how would I find t1? Well, it's really important to remember this because you've probably already encountered it by now. But at the max height, the y velocity is 0 by definition. Okay, because at the max height, you've stopped moving upward and downward at that point, right? You're no longer moving upward. If you were, you would not have reached your max height. You're not already falling down, because if you were, then you'd be coming down from your max height, and you also would not be at your max height. And so Vy at t1 is equal to 0. That's because we have a turnaround point along the y direction, and so the velocity in the y direction has to cancel. Okay, so this has to be true. And again, if I write enough things that are true, I get my answer. But, so I'm going to solve for t1 with this, and then I'm going to plug t1 into x of t and y of t and get my answer. Right? So it's not like, it's a straightforward question, I get it. The point I'm trying to make here is the following. The point is that it is much easier to conclude this, that this has to be true. In other words, it is a lot easier to write things that must be true than to say, you know what, just by looking at this, I know exactly what I'm going to do from A to Z to get the answer. I don't know t1, so I'm going to find t1, I'm going to use a kinematic equation, and then I'm going to plug t1 into x and y. That's going to be the answer. Now, I'm not saying you can't get to that point. You can with enough practice, absolutely, but it's really hard to get there. And it's not necessarily the goal of Physics 8A to get you there. The goal is to be able to do this. And once you've done this, you can start to solve. You may not know that first you're going to solve for t1 and plug into x and y, and that's going to be the answer. That's okay. Just start solving. You'll see. You'll get pieces of answers, and then you can move forward. But it's very hard to visualize the solution from A to Z, you know, the whole strategy. That's very hard to do, as opposed to just this. This is very easy to do. But it's a very different way of thinking of things, and you're used to classes where you know every step you're going to take from A to Z, right, to get the answer. And so we're going to try to focus on this when we do these live streams, because we're learning how to set up problems and how to think of how to solve them. We are trying to write things that are true, and from that we're going to get the answer. We just kind of have to trust that even though this doesn't really look like an answer, it will give us the answer in the end. Okay, so let's solve Vy of t1 is equal to 0. Okay, well, Vy of t1 is minus g t1 plus v naught sine theta. Okay, and again, I'm going to do everything in variables as much as possible because, first of all, it's good practice. It's how you should do it anyway. You might not have a choice on the exam also anyway. And I'll plug in values last because occasionally you do have values, and for the homework you need to be good at plugging in values, but we're going to try to use variables as much as possible. So if I throw gt1 to the other side, I'm going to get gt1 is v naught sine theta. All I would have to do then is divide v naught sine theta by g. That ought to give me t1. V naught sine theta it doesn't matter actually. I'm going to leave it like this because I could get a number and I could then plug a number into x of t and y of t, but just to practice variables, I'm going to plug in t1 as v naught sine theta over g. Okay, so that's the time it takes to reach this point. Again, once I have time at kinematics, I know everything. I know position, I know velocity, and so on. So first of all, we're going to say that y max is going to be y at time t1. All right, now by definition, this is minus 1/2 of g t1 squared plus v naught sine theta t1. Okay, well, we just found t1, right? So this is minus g over 2. t1 squared is going to be v naught squared sine squared of theta divided by g squared. Comes from here, yeah? Okay, if you have ab over c and you square it, you get a squared b squared over c squared. And then plus v naught sine theta multiplied by t1, which is v naught sine theta over g. Okay, so this is going to clean up nice, actually. We're going to get g is going to cancel the squared. I'm going to get minus 1/2 of v naught squared sine squared theta. This is going to be v naught squared sine squared theta. And so to get the same denominator, I'm going to, well, that's a little fast. Let's do this. Let's not skip steps. If I, you might end up becoming a Berkeley professor if you skip too many steps in solving. So v naught squared sine squared theta over 2g minus the whole thing, of course, plus, well, this becomes v naught squared sine squared theta over g. And what I was trying to do, but it's kind of a little quick there, is to get the common denominator 2g to show up so that I could figure out that y max is equal to v naught squared sine squared of theta divided by 2g. Okay, and so we can conclude, let's put it down here, and you should always box your answers. This is v naught squared sine squared theta over 2g is equal to, now v naught is 10, so 10 squared sine squared of 50 divided by 2 times 9.8. Now I definitely need a calculator for that. Sometimes you'll be given values that you can compute off the top of your head, which is nice. But this, you need a calculator, and you're going to find about 3 meters. Something like that. Okay, that's the max height. At what x location, because there's a two-part question, yeah? We are looking for this, which we just found is 3 meters. We're also looking for this, the x location where it occurs. Okay, so that's just going to be x1 is equal to x at time t1, which is v naught cosine theta times t1. Okay, and so that is v naught cosine theta multiplied by t1 is v naught sine theta over g. So we wind up with v naught squared sine theta cosine of theta divided by g. And so finally x1 is equal to all of this, and we have all of the values, we can plug them in. It is going to be 10 squared sine of 50 first, cosine of 50, there we go, divided by 9.8. And then that's going to be approximately, that's about 5 meters, give or take, if you accept a little bit of rounding. Okay, so that's where he is when he reaches his max height of 3 meters. Okay, so very classic, yeah, very classic to just solve for time and then plug time into something else because that's really what you want. It's a very common way of solving kinematics questions. So that's for question 2. Question 3 wants us to find the time of flight. Okay, so I'll come do this down here. Question 3, the time of flight. Now this is, again, this is not the path followed by the ball as it flies through the air. It is the path followed by Tony Parker. So Tony Parker does not go through the hoop, right? And he lands somewhere here, I don't know where, at a time, call it T final, right? T sub f, which is, you know, the total time spent in the air, sometimes called the time of flight. Same thing, right? It's the time between leaving the ground and hitting the ground again. All right. Now, there's a very similar approach for all these questions, which is, if we scroll up, forgive me for the scrolling real quick. If we scroll up here, what we tried to do is we tried to write things that are true at time t1. And in terms of x and y, it was pretty easy. And then in terms of velocity, we were able to say that vy at t1 is 0. Which is true because it's a turnaround point. You're not at your max height if vy is not 0. So then the question is, well, okay, what could we write, you know, at time t final, right? If we were to write at time t final, we have, well, what do we have? Now I can't really say anything about x because, I mean, x here would be called the range, typically denoted by capital R, but I don't know what the range is equal to. Now I could find it. If I knew TF, I would plug it into x of t to get the range, but I don't know what it is, so it doesn't really help me. So yes, x of t final is r, but I don't know r. Y, at this point, hopefully we agree, is going to have to be 0. Okay, because now we're back on the ground. Okay, one thing that is an extremely common mistake, and I see it all the time, it's very tempting, is to say, oh, well, when Tony Parker hits the ground, his velocity, Vy is going to be 0. Probably Vx is going to be 0 too, because he stops. It's like, well, no. You cannot say this, right? Upon impact, whether it's Tony Parker hitting the ground or a cannonball hitting the castle wall, upon impact, velocity is never 0. That's why it's an impact, right? Now, after the impact, yes, that's true. After Tony Parker hits the ground, he will come to a stop. So if I wait just a little bit more, he will come to a stop. But if you manufacture cannonballs that hit the castle wall with 0 velocity, you've manufactured the shittiest cannonballs in the history of mankind. That's not why you build cannonballs. You build cannonballs so that they strike the castle wall with as much velocity as possible so as to destroy it. Okay, so upon impact, velocity is never 0. So you can never make a claim about the velocity of something landing on the ground, trying to say, well, the tennis ball fell in the snow and it stopped, so velocity is 0 upon impact. No, that's why the velocity is not 0 upon impact. That's why it made an imprint in the snow. After it hit the snow, velocity was 0. So careful with that one. That's a subtle one. It's a very tempting mistake. So the only thing that I know to be true for sure, that's that's helpful anyway, is y at t final is 0, right? Okay. Well, so what does that mean? Well, it means that this minus 1/2 of g t final squared plus v naught sine theta t final has to be 0. Now keep in mind, my unknown is t final. That's what I'm solving for. And it shows up squared and not squared, which means more likely than not I have a quadratic. However, this is a nice quadratic because it has no constant term. In other words, there's only a term with t squared and a term with t. There's no other constant term in the way. So I can't do this with every quadratic, but with this one I can. All I have to do is factor out t final, and I get t final times minus 1/2 gt final plus v naught sine theta is equal to 0. And if I have that, then I can say a product of terms is equal to 0 if and only if at least one of the terms is 0. So it is either the case that t final is 0, or it is the case that all of this is 0. And of course, t final equal to 0 makes no sense. T equals 0 here. Now, is y equals 0 when t equals 0? Sure it is. Mathematically, it's a great solution. But math doesn't know that this is when Tony Parker started jumping. Math just says, hey, you asked me when y is 0. I'm telling you, it happens here and then somewhere here. But I have no way as math to tell you which solution you should neglect or not. I'm just telling you what the solutions are. So the physics part, of course, tells you that we ignore this because this is not when, well, this is not the time of flight. You haven't started flying. This is when you're leaving the ground, right? So we ignore this, and it leaves us with 1/2 of g t final is equal to v naught sine theta. And so therefore, t final is equal to 2 v0 sine theta divided by g, which, if you've been paying attention, is 2t1. Right, t1 being the time it takes to reach the max height. Now you gotta be super careful with that one, okay? Because, and by the way, we have, oh, I need to compute that. So I'll compute that in a second, sorry. I didn't compute that. I'm gonna box this just because it's an important result, but I'm also gonna compute and box the answer, the numerical value. T final is 2t1, okay, is only true, and pay attention, okay, I'm going to say it again for those in the back. T final equals 2t1 is only true because this parabola is symmetric. So if this is t1, the time it takes to go from here to here will be the same time as it takes to go from here to here, okay, but it is only valid because you start on the ground and you end up on the ground, okay. If this guy, if Tony Parker were jumping onto, a platform, then you could not claim that the time to go from here to here is the same as the time to go from here to here. It's not true, right? So you have to be super careful before you start using this t final is 2t1 thing. It's very tempting to want to use it, but it's only true if you have a symmetric parabola, right? You have to have the same amount on both sides exactly so that you can claim this. But if it is the case, then sure, you can say that. Okay, so what is t final? Because we didn't compute t1. So t final is 2 v0 sine theta over g. That is 2 times 10 times sine of 50 divided by 9.8. And that's approximately equal to 1.56 seconds. Speaking of which, and now I'm remembering, another common question that I got is, how do you know to put your calculator in radians or degrees? Okay, easy to forget that if you don't do it a lot. Don't overthink it, okay? Degrees or radians is just telling your calculator the angles I am providing inside of cosine and sine and tan are in degrees or in radians. That's all you're doing, right? Now here we're in degrees because 50 is given in degrees. So you wouldn't want to have your calculator in radians while putting in sine of 50, because your calculator is going to be like, ooh, sine of 50 radians, okay. And you're going to get the wrong answer, obviously. Right? So don't overthink it. It's straightforward. It's just be careful, because a lot of the stuff we're going to do at the very beginning of 8A is full of degrees. It's just, we just understand it better, right? It's more common. But at some point, we're going to have to switch to radians, because that's going to be the right unit to be using when it comes to angles. So for now, though, degrees all the way. Okay, so T final is 156. That is the time of flight. Okay, and then we're going to try to, I should have enough room here. We're going to try to fit the last question here, between here and the next page. Now the next question, so I really like this question. You see why. So the next question says, how much time does he spend at a height greater or equal to 3/4 of y max? Okay, so here's not a very classic question. All the questions that we've done so far, finding the max height, the time of flight, even finding the range, are very classic projectile motion questions. But this one is kind of unique to this problem. Okay, so we know that the max height, right, is y max, which is about 3 meters. Okay, so let's take 3/4 of that, wherever that is. I'm just going to draw a horizontal line like this. And I'm going to say, well, this is 3/4 of y max. Okay, just as a visual representation. Okay, so this is 3/4 of y max. There we go. And we want to find the amount of time that he spends above 3/4 of y max. So we want to find the amount of time he spends here. Okay. Now we can find that because what it would be is just, if I happen to know the time, let's call it T2 here and T3 here, then all I would have to do is compute T3 minus T2, right? Now how would I find T2 and T3? That's the great question. Okay, now that question is answered by solving. We're going to solve y of t is equal to 3/4 of y max. That's it. That's what we're going to do. Okay, now 3/4 is 0.75 if you prefer to write it that way. I'm going to leave it as a fraction, okay, because we're going to review quadratics, and this time we're going to have to solve with the quadratic formula. Okay, so we're going to solve that. It should give us two solutions. It should give us T2 and T3. I'll take the bigger solution, subtract the smaller solution from it. That's going to give me the time spent above this height. Okay, so I am solving minus 1/2 of g t squared plus v naught sine t is equal to 3/4 y max. All right? Okay. So let's put everything on the same side, left side or right side. I'm going to throw everything onto the right side. So if I throw everything onto the right side, I get 1/2 g t squared minus v0. I forgot a t now, didn't I? There's a t right there, my bad. Sorry about that. Hold on. Fix that real quick. There we go. All right, minus v naught sine theta t plus 3/4 of y max is equal to 0. Now this is a true quadratic, okay? I have this term here, so I can't just factor out t and solve. I just have to use the quadratic formula. I really don't like fractions. If I could get rid of fractions, that would be nice. So I'm going to multiply everything by 4. So I'm going to get 2g t squared minus 4 v0 sine theta t plus 3 y max is equal to 0. Okay. And then from there, we're going to solve this with the formula for the quadratic, right? So quick reminder here, this term here is a. This term here, minus included, is b. and then this term here is c, right? If you're arguing something of the form at squared plus bt plus c is equal to 0. Okay. And as a reminder, yeah, just real quick, not x because the unknown is t really. T would be minus b plus or minus square root of b squared minus 4ac divided by 2a. Now, usually if you're lucky, that's going to be on the formula sheet along with the exam. I wouldn't venture into the exam room without knowing this off the top of my head. It seems like an unnecessary risk, given the likelihood that you are going to end up with a quadratic. Okay, so let's solve this thing. This thing has two roots. I don't know which one is t2 and t3 yet. I'm going to just call it t both cases. So t is going to be equal to minus b, that is 4 v0 sine theta. And then I'll do the minus square root first. So minus the square root of b squared, that is 16 v0 squared sine squared of theta, minus 4 times a times c. 4 times 2 is 8, times 3 is 24, so this is 24 g y max. Okay, divided by 2a is 4g. Or the exact same thing with, in front of the square root, a plus instead of a minus. Okay. Now, which one's bigger? So that's pretty easy. Here you subtract this, here you add this. So it stands to reason that this is going to be t2, this is going to be t3. If you plug in all the values, you're going to find that this is approximately 0.4 seconds, but we know everything that we're plugging in, right? So I would recommend you do it just to practice plugging stuff in. The number of questions I get about the homework where I get a message from one of the students in the masterclass like, it's not working on Expert TA. Is like, well, because you've got your parentheses off. So I know that most exams are variables only, and very likely you won't have to worry about crunching numbers during the exam. But in case it ever happens, you got to practice parentheses. Okay, you can't just go in there and not know how to properly allocate parentheses to define a numerator, a denominator, or a square root, or things like that. So practice this. You should get 0.4 for this. You should get about 1.17 for this guy. Okay, neither of these is the answer to the question, right? Remember, the answer to the question is t3 minus t2. Okay, so the time spent above 3/4 of y max is equal to t3 minus t2, which is 1.17 minus 0.40, and that's approximately 0.77 seconds. Okay, now quick reminder, the total time of flight, the total time spent in the air is 1.56 seconds. Okay, so half of the time spent in the air is spent above 3/4 of the max height, right? So half the time spent in the air is just spent in this region here. That is actually why basketball players, when they dunk, they appear to float in midair, right? Because half of the flight time is spent above 3/4 of the max height. So they look like they're suspended there for an instant, then boom, they come down. That's because of the fact that that's the portion of the motion where you move the slowest, because you have the slowest upward and downward velocity on those portions up and down. You move forward at the same rate all the time, right? Vx is constant because Ax is 0. But that's why they appear to be suspended in midair. So that's the Hopefully that makes this problem a bit more interesting and more relatable. But have a look on TV again. If you didn't notice it, you'll see it. It's a cool little feature. So with that said, this is a very straightforward problem. Like this, if you get this on an exam, this is someone being nice to you. Right? So I'm not trying to scare anyone. I'm just trying to set the expectations right. This is me being super nice to you. This is whoever's teaching, Lowhorn, Golightly, whoever, being super nice to you. Not saying it's not going to happen. Not saying you're not going to get an equivalent problem that's about the same difficulty, but expect to see, at least in practice, harder projectile motion questions. And you should practice them as well, because projectile motion, kinematics in general, is usually a chapter that everybody hates. I think it's that is because the first chapter that you've done in physics. I think that's why. Nonetheless, you usually don't like it. But I promise you projectile motion will show up again and again. I promise you it will be on midterm 1 in one form or the other, and that there are harder problems than this as well. So make sure you practice and you feel comfortable enough with it, because it's going to be well worth it to put in time now. It'll pay off not just midterm 1, but also later, all the way through the final in some cases. All right, so that takes care of that guy. Let's do another problem, right? And we're going to go a little bit faster at first, because the first two questions are the same, right? It's just what I'm trying to do here is, I don't want to change everything at once, and then you can't tell apart what changed and was easy and what changed and was hard and whatever. So my goal here is to kind of, let's get good at setting up kinematic equations, so we'll do that. And then let's solve the x location for the max height of the ball, and we'll see how to do that. It's a bit of a conversation to have there, because it's not strictly identical to what we just did. But let's also figure out what happens if there's something that you wish you knew that you don't know, and how you deal with it. Like, what happens, okay? Because in the previous problem, we knew V0 and we knew theta off the bat. It's very common to give you that. Those are the easiest projectile motion problems. If I want to make your life a little bit harder, I'm either not going to give you V0 or I'm not going to give you theta. And if I'm really in a bad mood, I'm not going to give you either. Now that means I have to give you other stuff, right? Because you need V0 and theta to answer these kinematics questions, which means that I need to give you more information so that at first you go solve for V0 and or theta, and then you can come back and say, okay, thank you, I now have V0 and theta. Can we answer the classic kinematic questions? Okay. So what do we have? We have a batter that hits the baseball with an initial velocity V0 at an angle theta of 45 degrees above the horizontal. Now the ball is hit at a height 1.2 meters above the ground. Did that on purpose. We'll see why. And then reaches a maximum height that is known, that is 24.15 meters. Okay. And then we have an outfielder at 81 meters from home plate, which is the origin. And we know the following about the outfielder. He can catch a ball up to a height of 3 meters if he jumps vertically. Now, he can catch a ball up to a height of 2 meters if he's just standing, in other words, does not jump, or running at constant speed, and presumably also not jumping upward, just running to get to the ball. Okay? And so we first want the kinematic equations of the ball's motion. What are the unknowns? Let's solve for them. Okay, so let's start with what we know. This is projectile motion. X is to the right, y is up. Okay, so ax is 0, we know that, and ay is negative g. Okay, so ay is negative g, like that. Okay, then same components as before. This is going to be v naught x, which is v0 cosine theta. It's the adjacent component. This is the opposite component along y, so v naught sine theta. And then be very careful, the origin here is chosen for you. It is at the x location from where the ball is hit. So this is x naught is equal to 0. However, y naught is going to be h naught. Okay, because now I hit the ball a certain height h naught above the ground. So I need to incorporate that into my equations. So yes, it's the same question as before, set up kinematic equations, but slightly different because we have slightly different initial conditions. A lot of them carry over and are the same, but there's a slight difference. So with all that, let's just write our kinematic equations. Okay, so let's see if I can, I'll do my best here. So, okay, so x of t is 1/2 ax t squared, that's 0, plus v naught x t, and that's v naught cosine theta t, plus x naught is 0. Okay, and then in the y direction, y of t is equal to 1/2 a y t squared, that's minus 1/2 g t squared, plus v naught sine theta t, that's v naught y, careful, plus the initial height h0. Those are the kinematic equations for position. Let's also write down the kinematic equations for velocity. Vx of t is just going to be v0 cosine theta, the velocity along x is constant. Vy of t is equal to minus gt plus v naught sine theta. Okay, those are my kinematic equations for this problem. Okay, so now I can answer any question about kinematics if I know v0 and theta. Because I know g, right? I know h naught, but I need to know v0 and theta to figure out x, y, vx, vy at any time. And so that's why the question says, well, what is the unknown and can you solve for it? Now the unknown is not theta. Theta is 45, so we cool. Okay? Now the unknown is v0. We have to solve for it. Like, okay, well, v0 is unknown. Okay, so that first answered that question. Then how do we solve for it? Okay, let me make a copy of this just so that we can carry it around and reference it as we go. Okay, make a copy of this and put it down here. And we don't need it to be huge, we just need to be able to see it. Okay, and the question then is, if you're not going to give me v0, you have to give me enough information so that I can solve for v0. Okay, but you know, before in the previous problem, we weren't given, for example, y max. Here we are. Okay, here we're given more information too, so there's a lot of stuff that we're given, and we got to figure out what to do with it and how we can solve for v0. So this is a great question because it does happen from time to time, and there's no way around it. You can't be like, oh, you know, screw it, I'm going to do question 2 and blah blah. No. You have to solve for v0. Now the only reason why you would say no, I'm going to move on to question 2 is that you've tried to solve for v0, you have no clue how. Then you take your pen, you write on your exam, say, I know I have to find v0. I can't seem to figure out how to do it. So let me just call it v0, and I'll show you how I'll answer all the other questions if I knew v0. I just don't, but I'll at least show you that I know how to do those questions. Okay, so you could do that, but you want to find v0 and theta if you don't know either. Here, we just need to solve for v0. So what's true? Well, look, we have information about y max. It's not bad. I mean, look, it's something anyway. So we can use this maybe, because here we also know that vy is equal to 0, right? Because it's the max height. By definition, you're not moving up or down at that moment, right? So maybe we'd called the time t1 before. It's a pretty good name for it, so let's keep t1. And let's see what we can say about this. Now, I can say a few things. I can say vy of t1 is equal to 0. That's true. That would allow me to solve for t1 like before. I could say y of t1 is y max, which is not bad because I know y max, but then I get to solve all of this equals y max, which means I get to solve a quadratic. And like, ugh, do I really want to do that? And the answer is no, probably not. But is there another way? Like, because I don't know x, right? And Vx is just constant. It's always V naught cosine theta, so that's boring. It's not going to tell me anything. So is there another way? I could find T1, yeah? I could find T1 by solving this equal to this. But the problem is it'll be in terms of V0. So it's like super annoying. So I'm not saying I couldn't do it with the equations that I wrote. What I'm trying to suggest is that there's a different way of doing it that a lot of times we don't think of, because we tend to think of the boxed equations here as our only kinematic equations we're allowed to use for projectile motion. And it is true that they work. It might be painful to solve, but they will always work. However, there's a faster way in this case. Okay, let's leverage the fact that we know that the y component here of velocity is v0 sine theta. Okay, we don't know v0, we want to solve for it, so we do want to have it in our equation. And here vy is 0. And then the change in height from here to here is actually known because I know y max and I know h0. And of course I know acceleration. So where am I going with this? I'm going to use this. I'm going to say that v final y squared is v initial y squared plus 2 ay delta y. Okay, that's the kinematic equation that bypasses time. So if time is irrelevant, we don't care about solving time, this is a good one to use if you know acceleration, displacement here in the y direction, delta y, and the velocities, right? Or at least one of these you're trying to solve for and you know everything else, right? So v final y squared is 0, right? That's going to be here. That's going to be the final location. This is going to be the initial location. So v naught y squared is v naught squared sine squared of theta. And then plus 2 ay is negative g. I know that. Let me move down here. And then what's delta y? Well, delta y is the change in y. Okay, well, your final y at the very top is y max, minus your initial y is actually h naught, not 0. So what do I get? I get v naught squared sine squared of theta is equal to 2g y max minus h0. How do I get v0? I just want v0, right? I'm going to divide by sine squared theta, and I'm just going to keep the positive root because v0 is just a speed, it's the magnitude of velocity. So this divided by sine squared theta, keep the positive root, and there you go. And now I've found v0. I know everything here, right? So this is going to be square root of 2 times 9.8 times 24.15 minus 1.2 divided by sine squared of 45. And that is going to be approximately equal to 30 meters per second if you plug in all these numbers and you crunch them. All right, that's v0. And this is still the first question, right? We set up our kinematic equations. We said, ooh, v0 is unknown, and then we solved for it. And we used the additional information we were provided to solve for v0. Okay, so now I know v0, I know theta, I have my kinematic equations. Ask me anything, I can solve it, right? So where along x does the ball reach its maximum height, y max? That's a really good question. Let's take this here again just so that we can look at it. Okay, we want the location x here, right? We had called it x1 earlier because we had said that the time t1 here is when you reach the max height, so that's pretty good. I'm going to stick with that. And I'm going to then solve for this location. Now, again, at time t1, what is true? Actually, the same things as before, yeah. So it is true that x of t1 is x1. So if I only knew t1, I would be able to solve for x1. Y of t1 is going to be y max, which is kind of cool because I know y max, so I should be able to solve for t1 there, now that I have v0. But it's also true, isn't it, that vy of t1 is equal to 0. Okay, so why am I writing all this? Let's have a conversation. First of all, you have to be able to write this, so let's start with that. But second of all, let's look at what we have. We're claiming that x1 is x of t1, which is v0 cosine theta t1. And so as soon as I know t1, I know x1, and I've solved the question. Fine. Then y of t1 is equal to 0 is actually, let me just write it out, y of t1, the whole thing is minus 1/2 gt1 squared plus v0 sine theta t1 plus h0, can't forget that, is equal to y max. Okay, but fine, the only unknown is actually t1, because I know v0, I know theta, I know g, I know h0, I know everything. So I can solve for t1. The price I must pay to solve for t1 is to solve this quadratic. Okay, but then the third equation is vy of t1 is equal to 0. And that's simply minus gt1 plus v0 sine theta is equal to 0. Okay? So I don't shy away from challenges, and I know that my audience typically doesn't either. That's why the bulk of it is pre-med or pre-dental or something like that. But if you honestly think that given the choice between solving a quadratic and just solving, a linear equation here for t1, I'm going to go solve the quadratic, you're out of your mind, right? I get to choose what I solve. These are all true statements. And if you prefer to go with the quadratic, don't let me talk you out of it, but you usually run out of time on exams, so we're going to go with the fastest option, which is to solve the third equation for t1. Once I have t1, I'm going to plug it in here, and we're going to get x1, right? So sometimes it's worth taking a few seconds and writing down what you know is true, and then from there, give it some thought. Say, okay, well, if there's more than one way to get t1, like let me choose the fastest one. Sometimes there's not. Sometimes you just have to bite it and solve the quadratic. We did that before. But in this case, there is. So first things first, we are going to solve this thing here for t1. All right, so we're going to solve that. We're going to find that t1, we did this before, so I'm going to go a little faster. It's v0 sine theta divided by g. And I know everything, so I could compute it, but I'll just leave it like that because I don't even want to bother computing it. I'm going to say x1 is v0 cosine theta t1. That's equal to v0 squared sine theta cosine theta divided by g. And now I can plug stuff in and get the answer, right? So this v0 is 30 squared sine 45 cosine of 45 divided by 9.8, and that's approximately 45.92 meters. That is the x location where the ball reaches its max height. Okay, there we go. All right. So, having said that, having solved that rather, we have two more questions, which are kind of interesting questions because now they bring into play this outfielder and what we know about him. And so let's paste this real quick. Okay. Now the outfielder has the following characteristics. He can jump, if he's standing somewhere, he can jump vertically upward. and grab a ball that's 3 meters above him. Or if he's running, he can only catch a ball that's 2 meters above the ground. Now apparently YB is 2 meters, right? So that means that if he runs to point B, so long as he makes it there in time, he can actually just grab the ball. For sure he can catch it at B if he makes it to point B on time. Question is, for question 3, can he catch it at point A when it's right above him, right? And so if the outfield jumps vertically, can he catch the ball when it is at point A? And assuming it's, point A being directly above him. So let's call this time TA, right? And let's see if we can figure it out. Basically, what is the height of the ball at time TA, right? If it's 3 meters or less, the outfielder can catch it. All he has to do is jump up. If it's more than 3 meters, jumping is not going to cut it, so he's going to have to run to point B or something, okay? So, same thing. We are in the business of writing things that are true. So at time TA, we have the following. Okay, what do we know at time TA? Well, not much, but we do know that x at time TA is equal to xa, which is 81 meters. Okay, so that means that V0 cosine theta TA is equal to xa, which means that this tells me TA. And again, this is kinematics. If I know time, I know everything. So I'm very happy with figuring out TA, because if I know TA, I can then compute y of TA and compare it to 3 meters. Okay, so TA is xa divided by V0 cosine theta. That is going to be, oh, that's it, I didn't even compute it. I just plugged it in, right? So that's what I get. And if I plug it in to y of ta, or y of t, I get ya. So y at a is y at time ta, that's what that is. And that is going to be equal to minus 1/2 g ta squared. Okay, well, ta squared is xa divided by v naught cosine theta squared plus v naught sine of theta multiplied by ta, which is xa, divided by v0 cosine theta plus h naught. That didn't go away. Okay, so that's just minus 1/2 g ta squared plus v naught sine theta ta plus h naught. And that's what we want to figure out and compared to 3 meters. Okay, and yes, I know you think I'm torturing you because I'm doing variables only. I'm really doing you a favor in the long run. Thank me later. I could compute TA and then just, find it here and then plug it into here with a number. I could do that. You could too. But more likely than not, if you look at an answer key that's been written by anybody in the physics department or GSIs, you're going to see this. Okay, so let's just practice variables and get comfortable with them as quickly as possible. It will make our life a lot easier, not just for this class, but for 8B if you have to take it. So let's do this. It's going to be minus g xa squared divided by 2 v naught squared cosine squared of theta plus v0 goes away, sine over cosine is tan of theta times xa plus h0. Give me a hot second, I will be right back. Apologies for the interruption. My dog was taking a nap and I think got bored of me doing physics in the same room, so she needed to be relocated. Anyway, and she can't open doors, obviously. So we were computing this and plugging in all the variables. And now basically we just plug in the values, and so it's going to be minus 9.8 times 81 squared divided by 2 times 30 squared cosine squared of 45 plus tan 45 XA is 81 plus 1.2. Now this is going to be 10.76 meters, which is much bigger than 3 meters. And so he cannot catch the ball at point A by jumping. Okay, that's not going to do it. Okay, so this is a question that is not a classic projectile motion question. Obviously, it is specific to this problem, right? Again, some questions are very common and across all projectile motion problems: time of flight, max height, range, things of the like. You know, angle that maximizes the range. All of those are common questions, but then invariably you end up with problems that, you know, they are what they are and they were written a certain way, and there are questions that are specific to these problems that you need to address, and you need to be comfortable doing that too. So he cannot catch the ball at point A. Question 4 then says, well, if he runs to catch the ball at point B, how long can he wait after the ball is hit before he must start running? Okay. Now, as a reminder, let's just paste this in here again to have something to look at. The outfielder can run at constant speed 5 meters per second. Right, so V1 is 5 meters per second. Okay, but that's constant speed, and he can catch a ball that's a height of 2 meters at that point. And so for sure at point B, that's when the ball is at a height of 2 meters. So you just got to get from A to B, okay, or XA to XB. Okay, so first things first, how long does it take him to go from here to here if he runs? Well, he's got to travel 10 meters at 5 meters per second. It should take him 2 seconds, right? So to travel XB minus XA equals 10 meters at V1 equals 5 meters per second, the outfielder needs to run for 2 seconds. So it's going to take him 2 seconds to get to point B. Right. Now let's see how long it takes the ball to get to point B. Because if it's less than 2 seconds, by the way, he's cooked. He's not going to catch it. Right. If it's more, then, you know, he's got to time it right, but he can make it. So let's see. What do we know at point B? You know, let's call the time TB at this location. What do we know that would help us figure out TB? Because that's really what we want to know. We want to compare that against 2 seconds. Okay. Well, so I don't know what TB is, but that doesn't mean that I can't write this. I can write that at time TB, we have the following. And it's okay if I don't know TB yet. That's probably how I'm going to solve it. So I have x of TB is equal to XB, right? And I have y of TB is equal to YB. Turns out I know both. XB is 91 and YB is 2 meters. Okay, so I have 2 equations that I can use. I can use V0 cosine theta TB is equal to XB, and then minus 1/2 GTB squared plus V naught sine theta TB plus H naught, don't forget that, is equal to YB. All right, well, pick your poison. You know, both have only one unknown, which is TB. And I'm not solving the second one. That's a quadratic. Like if I have to, sure. But if I don't, no. So I'm going to solve the first one. I'm going to get TB there. I'm going to say, okay, well, based on what I wrote up here, TB is just going to be equal to XB divided by V0 cosine theta. That is going to be 91 divided by 30 times cosine of 45, and that is going to be 4.29 seconds. Okay, so at least it takes the ball 4.29 seconds to get to point B, and since it only takes the outfielder 2 seconds to run from XA to XB, okay, he can actually catch the ball. And in fact, the longest he can wait is 2.2 seconds, the difference between the two, right? So the outfielder can wait TB minus, well, I didn't name the other amount of time, so can wait 4.29 minus 2 is equal to 2.29 seconds before he starts running to catch the ball at point B. All right, so that's my answer, right? And again, this is a question that's specific to this problem, but with knowledge of kinematics and by writing down what I know at a certain point, I can solve for things that allow me to get to the answer. And so that's really what I want to kind of emphasize, right? We're trying to do a few things with these live streams here. We're trying to summarize very briefly what is important from lecture, because that's kind of the easy part. It tends to, you went to lecture and then you went to discussion, and some of you probably already summarized it all. And that's the easy part. The hard part is to then take a problem and sit down and learn how to set it up, right? And there's a lot of components to that. There's setting up a problem, labeling things like calling time TA, TB, things like that. That's something you have to get used to. And then there's, determining what is true in certain cases or at a certain point. And sometimes things are true that you don't need, but if you write enough things that are true, typically you end up with enough material to solve the question. You just have to put it all together. And of course, you have to realize that. And again, it's not a very natural way of thinking about solving a problem. We tend to, even in the real world, we don't, solve a problem until we stumble upon the next, roadblock, and they're like, okay, well, now I'm going to solve this, and then you don't know. Like, you usually know where you're going, and you usually know how you're going to get to the solution. Now, that doesn't mean that you don't have to solve unknown situations along the way, but we always tend to have a map that takes us from where we are to a solution. And yes, things might change along the way, but still we have a map. Here, what I'm trying to argue is that we don't. You don't need a map. You just need to write things that are true, right? And eventually, if you put them together, you can then say, oh, well, this is the answer, right? And it's a lot easier to do that in physics, to just write things that are true, than to try to visualize how you're going to get from point A to point Z, which is a solution, and what steps you're going to follow and how. Now, I'm not saying you can't do it. Again, it is totally doable. If you do enough physics, you will be able to do it. And it might seem maybe easy right now because all we learned about are kinematics. But trust me, this class has got a lot of content and it moves fast. And when you start putting everything together, it is very hard to say, oh, well, okay, I'm going to use circular motion here and then work in energy here. And then from kinematics, I'm going to drive a distance that'll complement all of that and then get the answer. Something like that, that's hard to do. So we're not trying to do that necessarily. We are just trying to get comfortable with the concepts so that we can apply them properly, write things that are true, and get to the answer. So that'll be it for this week. Thank you for watching, as always. I appreciate it. Thanks for your questions. It's also fun to go back and forth and answer your questions, and I'll try to highlight the interesting ones that come up, or the ones that come up a lot. Sometimes it means that I missed something, or that there's something really confusing floating around. But keep up the good work. It's a hard class, again, because of little time and a lot of material. So don't let it catch you off guard. Don't wait till end of September to start reviewing midterm 1. That would be a mistake in my estimate. But stick with it. And if you've never taken physics before and you hate it, the goal is to hate it a little bit less by the end of the semester. But more seriously, don't get discouraged. It's one of these things. Once you do enough of it, it gets better. It does. And there's certainly some hard patches through 8A, but there's also some easier ones that come around. Circular motion is pretty easy. Conservation of energy is pretty easy. Once you wrap your head around torque, you tend to like it. And then thermo is actually great at the end. So there's some sunshine between the clouds there. And again, doing physics, it builds on itself. So there's a certain way to think about physics and to go about a physics problem. And by the end of the semester, you'll see that you're in a much better shape than you were at the beginning when it comes to thinking through physics problems. Which is, by the way, why I recommend taking 8B right after 8A if you can. If you can or if you can't, and you're wondering who to take it with, you can always hit me up and I can give you some advice. Although it seems like Berkeley doesn't want to produce the names of who teaches which section early enough for you to choose when you have to enroll. So, but if you take 8B right after 8A, I think you'll find it beneficial. Don't do what a few of my students have done that, they've suffered for it, is that they either waited for the last semester. One of them took 8A and 8B the last summer of their undergrad. Trust me, she was miserable, and she remembers that summer still. And she's a board certified doctor by now, but she still remembers that summer. And then I had one who took 8A fall freshman year, took 8B spring senior year, and she also remembers that. That was a tough one. So anyway, stick with it, just like everything else. If you do enough of it, you'll get good at it. And you can't read about push-ups, you got to do them. So physics is the same way. Thanks again for watching. Send me your questions. Keep in touch. I will see you next week for a new live stream. And for all the other ones, masterclass students, I'll be on in a second right after this. So talk to you soon. Take care.